Webb keeps spotting grown-up galaxies in a baby universe. Here's the immediate takeaway: our timeline for growth looks wrong. A telescope a million miles away is watching ancient light arrive. It sits beyond the moon's orbit, chilled in deep shadow. Its job was to confirm the story we already told. Instead, it keeps finding chapters that were never written. July 12, 2022, the first deep infrared image dropped. A grain of sand patch of sky erupted with thousands of galaxies. Several looked organized, bright, and massive, far too soon. The light left when the cosmos was only a few 100 million years old. Under standard models, there was not enough time, by a lot. Picture that first scene, a tiny speck of sky blazing. That field came from a galaxy cluster acting like a lens. Light stretched around gravity, forming arcs and sparkle trails. Astronomers call the distance measure redshift because wavelengths get longer. Higher redshift means earlier times, when the universe was younger. This matters because time is the currency for building structure. To read those times, Webb drinks infrared light, not visible. Dust glows there, and early starlight slides there while traveling. Its mirrors gather faint photons, then instruments split them by color. That split prints fingerprints, revealing age, motion, and chemistry. Mechanically, the telescope stares for hours, stacking whisper-faint signals. Software removes noise, and calibrations turn counts into flux. Then models convert light into stars, sizes, and distances. Example in real terms, some arcs came from redshift around 10. That is roughly 500 million years after the bang. Others pushed to 13 and beyond, even closer to dawn. The surprise was not only distance, but structure and brightness. Galaxies already looked concentrated, with bulges and clean outlines. Bottom line, the clock they implied ticked much faster early. There is a bolder claim people kept repeating: too massive. Stellar mass means how many suns worth of stars a galaxy holds. Stakes are huge because mass growth paces the universe's build. Observers estimated masses using how bright galaxies looked in infrared. Brighter often means more stars if dust and bursts behave. Then spectra refine ages by catching absorption features from older stars. Here is the catch: emission lines can fake brightness in images. Strong oxygen or hydrogen lines boost certain filters, inflating mass. Webb's NIR spec helps by separating lines from the underlying glow. Early headlines shouted galaxies with tens of billions of suns. Several later dropped to hundreds of millions or a few billions. Still, some remained hefty for such early times, which stings. Tiny test: could dark matter halos have formed faster than expected? Simulations show rare peaks can collapse early, though not everywhere. Gas then cools quickly, turning to stars with high efficiency. Real case: the JADES team confirmed galaxies beyond redshift 13. Their masses were around hundreds of millions to a billion. That is not impossible, but it is ambitious for that dawn. So the picture is challenging, yet not outright breaking physics. Now swing to shapes, because shapes tell a growth story. A disk galaxy is a flat, rotating pancake of stars. That structure forms when gas settles and spins in a halo. The interest is clear: ordered disks should take time to calm. Webb has spotted surprisingly tidy disks when the universe was young. Images show clean rotations and thin profiles at high redshift. Gas must have cooled fast, while turbulence surrendered earlier than forecast. Feedback from young stars did not fully tear these pancakes apart. One-sentence recap: order arrived alongside chaos, not long after dawn. Take a look at studies finding disks by redshift 3. That is 2 billion years in, with many already well settled. Some candidates even nearer to 1 billion years look organized. Are we fooled by lensed views sharpening what already exists? Sometimes yes, but several unlensed examples hold up on reanalysis. The mechanism could include cold streams feeding angular momentum steadily. Minor mergers can also build disks rather than only wreck them. Net result: formation pathways might be more efficient than textbooks suggested. Here is the heartbeat: stars were switching on at wild rates. Star formation rate means how many suns per year a galaxy builds. Stakes are direct: more stars earlier means faster chemical and structural growth. Webb revealed many bright ultraviolet galaxies at very high redshift. That light tracks massive newborn stars, which burn hot and blue. The counts rose faster than Hubble's extrapolations had predicted. Mechanically, teams measure a luminosity function, the tally of brightnesses. The curve seems steeper early, meaning more luminous newborn factories. Dust correction matters because soot can hide star formation brutally. Spectra show intense hydrogen lines, marking ferocious nurseries burning through gas. Example, several Z10 to Z12 systems churn tens yearly. A few extreme candidates peaked above 100 suns per year. Those numbers shrink with better models, but the trend persists. Quick check, could supernova feedback have allowed bursts then brief quenching? Bursts would explain bright flashes without demanding giant, permanent masses. Rule of thumb, early galaxies were small, but incredibly productive. Bottom line, the early sky was busier than most forecasts. Another shocker lives in the cores, heavy black holes shining. A quasar is a supermassive black hole, feeding and blazing. Why care? Because building huge holes fast strains our timelines. Seeds may start as heavy stars or direct collapse gas clouds. Then they binge on gas, doubling mass every few tens of millions. Radiation blows back, so growth cannot stay perfectly exponential forever. Webb has caught active nuclei in galaxies close to cosmic dawn. A standout is Sears 1019, an active nucleus at redshift 8.7. Its black hole weighs about 9 million suns, already hungry. Lines in its spectrum reveal accretion and energetic winds blasting outward. Several candidates push toward redshift 9 and beyond, still under study. Example continues, luminous quasars at redshift 7 host billion sun holes. Those existed earlier than comfortable models prefer them to appear. Pattern break, two routes could help, heavier seeds or faster fueling. Direct collapse seeds might start near 100,000 suns, skipping steps. Dense, gas-rich halos could then feed them close to limits. What to remember, early black holes grew fast in crowded kitchens. Chemistry adds another twist, metals appeared earlier than expected. In astronomy, metals mean every element heavier than helium. That matters because metals cool gas, shaping how stars and planets form. Spectra from Webb show oxygen and neon lines in young galaxies. Those require multiple stellar generations, exploding and seeding their neighborhoods. Oxygen-3 lines appear shockingly strong in some first billion-year systems. Mechanically, massive stars live short lives, then detonate as supernovae. Their debris cools, mixes, and triggers new, more metal-rich stars. You can see knots of ionized gas tracing violent, recent births. Real numbers, some galaxies show metallicities around a 10th solar already. Others are lower, but still non-zero at very early times. That does not shatter theory, but it compresses enrichment schedules sharply. One sentence wrap, the universe started its chemical factory almost immediately. So is the universe broken, or are our rulers miscalibrated? Selection bias means we often find the bright, rare outliers first. That skews intuition, especially when surveys are small and deep. Photometry can also be tricked by emission lines boosting broadband filters. Spectroscopy fixes many of these traps by isolating true continua. Dust laws at early times may differ from nearby galaxies. That changes how we translate colors into ages and masses. The stellar initial mass function might also tilt toward massive stars. If so, luminosity per mass rises and masses drop afterward. Example, several early monsters shrank once NIR-spec spectra were analyzed carefully. Redshifts moved, lines were separated, and masses relaxed downward. Yet not every tension vanished, some galaxies stayed surprisingly ambitious. Pattern note theory is updating too, with faster gas cooling routes. Simulations with bursts, clumps, and streams can reach Webb's numbers. Net result, the crisis softened, but the puzzle still stands. Those first images felt like hearing an echo from tomorrow. Webb kept spotting grown-up structures in a very young sky. The reasonable lesson is humble. Our timeline might need edits. Data are sharpening weekly, and models are bending to meet them. I love that science allows both tension and patience together. We learn by having nature grade our homework, then rewriting it. If this changed your picture of the cosmos, tell me. Drop a comment with the one result that stunned you. And if you want more space stories like this, subscribe. Bottom line, the universe was busy early, busier than we guessed.